A turning fork is stuck and oscillates in damped harmonic motion. The amplitude of the motion is measured, and 3 seconds later it is found that the amplitude had dropped to 1/4 of this value. Find the damping constant C for the turning fork. Notice that we were not told the amplitude, but it won't matter in this case. The general formula for the damping motions are y equals k e to the negative c t sine of omega t, or y equals k e to the negative c t cosine of omega t. The amplitude is governed by the factor k e to the negative c t, and we're looking for c with the given information. We were told that the amplitude is measured, and 3 seconds later it is found that it dropped 1/4 of its value. And so we set up a system of equation. When time equals 0, the amplitude is measured. We have a of 0 equals k e to the negative c times t, but t is now 0, so this is k e to the 0 power, or simply k, as expected, the initial value. And so the amplitude is k to start out with. After 3 seconds, the amplitude is found to be dropped to 1/4 of this value. We plug 3 into the amplitude function to get k e to the negative c. T is now 3, and this amplitude is now 1/4 of the initial amplitude k. And so k canceled out. We end up with e to the negative 3c equals 1/4. ln both sides of the equation, we get negative 3c equals ln of 1/4. And so c is negative 1/3 times ln of 1/4. We then put this in a calculator and find that c is approximately 0.4621. And this is the damping constant c in the damped harmonic motion. It doesn't matter whether we use sine or cosine, c is the same for both models. We got the answer by assuming that the amplitude was measured when time is 0, which might not be in this case. And so, to be a little bit more rigorous, we assume that the amplitude is measured when time is t1, and it measures again when time is t1 plus 3, that 3 seconds after. With this, we now have the system of equation a of t1, which is the first time the amplitude would measure, k e to the negative c times t1, which is k e to the negative c t1. For the second time, the time is now t1 plus 3 seconds after. The amplitude is k e to the negative c, but the time is now t1 plus 3. The goal is to find c. In this case, there are so many unknowns here, t1, k, c, but remember, we were told that after 3 seconds, whatever this amplitude is, k e negative c t1 plus 3, it is 1/4 of the amplitude that we measured the first time, which is k e to the negative c t1. The k canceled out, so we end up with e to the negative c t1 plus 3 equals 1/4 e to the negative c t1. And using the law of exponent, we have e to the negative c t1 plus negative 3c equals 1 over 4 e to the negative c t1. But then we can separate the sum in the exponent by rewriting the left-hand side at e to the negative c t1 times e to the negative 3c equals 1 over 4 e to the negative c t1, and e to the negative c t1 and e to the negative c t1 canceled out, leaving us with e to the negative 3c equals 1 over 4, which is the same as the equation that we obtained earlier when we hastily assume that we measure the amplitude when t equals 0.